Hello everyone. In this video, we will learn about the deadlocks, the system model and the deadlock characterization. The deadlock problem. That is a set of block processes each holding a resource and waiting to acquire a resource held by another process in the set is a deadlock. For example, a system is having two disk drives. The processes P1 and P2 each hold one disk drive and each needs another one. That's a deadlock. Also, the semaphores A and B, they are initialized to 1. In the process P0, it initiates a wait operation on A. In the meantime, process P1 initiates a wait operation on B. The next instruction is wait of B by the process P0 and wait of A by the process P1. As there is no signal operations on both the ends, it leads to a deadlock. System model. Resources may be partitioned into various types R1, R2 till Rm. The resources could be CPU cycles, memory space, I/O devices. Now each resource type Ri will have Wi instances. And when a process wants to utilize a resource, it has to make a request, use the resource and then release the resource. This request and release are generally done by the system calls using open, close file, allocate and free memory system calls. Generally, a system table is one which will record whether each resource is free or it is allocated. In case if it is allocated, it will record to which process it is allocated. So that information will be recorded in the system table. Deadlock characterization. A deadlock will arise if four conditions hold simultaneously. Now we will learn what are the four conditions. The first condition is mutual exclusion. Only one process at a time can use the resource. Hold and wait. A process is holding at least one resource and is waiting to acquire additional resources but that are held by other processes. No preemption. A resource can be released only voluntarily by the process holding it after that process has completed its task. Circular wait. There exists a set of processes where this P0 is waiting for a resource that is held by P1, that P1 is waiting for a resource held by P2, and P2, for example, if it is waiting for a resource which is held by P0 again. So that's a circular wait condition. Deadlock characterization, resource allocation graph. Generally, a resource allocation graph will have a set of vertices V and a set of edges E. Now, this vertices V is partitioned into two types. So, one is processes. Set of all processes will be represented as P. P1 to Pn processes will belong to that set. And set of all resource types will be specified in this set R, where R1 to Rm are the different types of resources. Now, in case of edges E, the edge could be a request edge or an assignment edge. A request edge means a process Pi is requesting for a resource Rj. It's a directed edge. The request edge will be like this. Pi is making a request to the resource Rj. Whereas the assignment edge, it's again a directed edge, but the arrow will be from the resource to the process, which means this resource Rj has been allocated to the process Pi. Now, in a pictorial form, the process will be represented by a circle and the resource will be represented by a rectangle, and the resource can have a number of instances. It can be of any numbers. For example, here this is a resource type which is represented as a rectangle and it has 4 instances in it, which means there are 4 resources. There are 4 numbers of that particular resource type is available. Now Pi is making a request to Rj, a particular instance of that Rj. If that is the case, the process is represented like this. It's making a request to a particular instance of this resource Rj. Pi is holding an instance of Rj, which means this resource Rj is assigned to the process. So now Pi is holding a particular instance of this particular resource type. This is a resource allocation graph. So in the resource allocation graph, if we want to represent the various sets, so the process P will include the set of all processes. This graph has 3 processes P1, P2 and P3. Set R includes the various resource types. There are 4 resource types, say R1, R2, R3, R4. And E represents the set of edges, both request edge and assignment edge. So P1 is making a request to R1, this edge, and P2 is making a request to R3. And as far as the assignment edges are concerned, R1 is assigned to P2, R3 is assigned to P3, R2 is assigned to P2 and P1. Now resource instances, how many numbers of that particular resource type is available? Considering R1, there is only one instance of resource type R1. There are 2 instances of resource type R2. There is only one instance of resource type R3. There are 3 instances of resource type R4. If we want to describe the process states, for example P1, we can describe the process state which includes both the request and the assignment. So it has to be like this. P1 is holding an instance of resource type R2 and is waiting for R1. Coming to P2, P2 is holding resources of type R1 and R2 and is waiting for a resource type R3. Whereas for P3, P3 is holding a resource type R3. Resource allocation graph with a deadlock. In case if a graph is containing no cycles, then no process in the system is deadlocked. There is no deadlock. If the resource type has only one instance and there exists a cycle, then there is a deadlock. And a cycle in a graph is both a necessary and a sufficient condition for the existence of a deadlock. But in case if each resource type has several instances and there exists a cycle, then it does not necessarily imply that a deadlock has occurred because so many instances are there. Cycle in a graph is a necessary but not sufficient condition for the existence of deadlock. For example, consider this resource allocation graph here. In case if P3 makes a request to R2, this P3 makes a request to R2, we are adding, we can find some cycles in the same graph, that is starting from P1, P1, R1, P2, R3, P3, R2, P1 is one cycle. Starting from P2, P2, R3, P3, R2, P2. This is again a cycle. Now I can say this processes P1, P2, P3 are deadlocked in this case. Now this is a graph with a cycle. Let us see how it will not lead to a deadlock. For example, in this resource allocation graph, you have a cycle, say P1, R1, P3, R2, P1. So though there is a cycle, there is no deadlock. It is because there are two instances here with R2 and currently P4 is holding one, and now P4 will release this resource instance of R2. So once it is released, that instance can be allocated to P3 and we can thereby avoid the cycle. So this is a graph with a cycle but no deadlock. Methods for handling deadlocks. First, we need to ensure that the system will never enter a deadlock state. That is, we need to go for a deadlock prevention or deadlock avoidance. Allow the system to enter the deadlock state and then detect it and recover. Or else ignore the problem and pretend that deadlocks never occur in the system. This is how we can handle the deadlocks. Thank you.